you enjoy the snow? You get snow in China, so... Or not China, sorry. Malaysia. You don't?
You get rainy and dry.
No snow? Oh, so this is new for you. Yeah, true. You get snow or no snow? Alright, so it was a new experience for you.
Always.
Well, you get snow in China.
Of course.
Yeah. Oh, it's not new for you. It should be new for you two, right? You don't get snow back home, I'd imagine. Not like this. Yeah. Yeah.
We have snow and we don't, and we will have traffic.
Yeah, not like Ireland.
This one we're all pretty.
Well, some parts of China get very cold.
Yeah. And continue with that.
And just continue, yeah. In China? No, snow's not so common in Ireland, believe it or not. Like that snow that we had last week. Yeah. The last time it was that bad. Yeah. It's not an annual thing. Yeah. It's not usual. Yes, you're lucky. Yes. Yeah. Okay, next lesson now. Latent heat. Okay. Got that title? Latent heat? Yeah? Okay. So, imagine a block of ice which is slowly being heated. That is, we put a fixed amount of heat per fixed amount of time. For example, maybe every second we put in 4,200 joules. For example. So, in other words, the power is 4.2 kilowatts. So the temperature of the ice will increase. Let's have a look at the graph of it. Whoa. So here's the graph. You start off with your ice, and as the energy increases, what happens to the temperature? Well, naturally it increases. So it starts at minus 100, then it increases until 0. But something very strange happens here at 0. Even though we continue to put energy into the ice, it's no longer getting hotter. And then afterwards it will start to get hotter again until we get to here. And even though we're putting energy into it, it's not increasing its temperature, and then suddenly starts to increase the temperature again. Now when you actually look at the temperatures, I'm sure you've figured out, or maybe not, what's going on here. So here, why is it not getting any hotter even though we're putting energy into it? Yeah, so like what's happening at this freezing point? So it's changing. Yeah, changing from what to what? Solid to liquid. And here it's actually changing from liquid to gas. In other words, you need energy to change the state from a solid, liquid or gas. This requires energy. And while it's changing state, the energy is not used to make it hotter, it's used to change the state. So this gives us the name of the lesson, the next idea. Now before we continue, they sometimes ask you to make this graph in the exam. What they want to see, you don't have to get numbers on it, except what they would like to see in the exam is that you at least mark this as 0 and you mark this as 100, obviously. And also what they expect the student to do is to make this longer than this. It takes more time and energy to change it from a liquid to a gas than it does from a solid to liquid. A lot more actually. So try and draw this. Don't worry about the exact numbers. Just make sure you have a 0 and a 100 marked here on the y-axis, and that this length is longer than this length. Well, I make everything look easy. It's my special ability. The x-axis is energy and the y-axis is temperature. Which one? Here? Change in state from ice to water. Guess what this one says? To steam, yeah.
It's only water.
Oh, this picture is just for water. Because obviously water is 0 and 100, but other materials will be different. But in the exam, they only ask you to do this graph for water. I need to answer this. It's something to do with my house. So give me one moment, please. Hello?
Yesterday? No. I went halfway and my friend told me that the cord is under the table. So it's kind of hurting. Then I reached the school. Then I stopped by the bus stop here and went to buy the fried chicken.
Yesterday we come to school.
Yeah, I was supposed to go to that thing called, but then my friend, after that, I arrived halfway and my friend told me it's cancelled, so I just stopped by the school and I just buy something and went home.
Why?
The cord is under the table. I was prepared. Like my hand, the beauty, no one costume. Come on. Give me money. I need money. Come in.
Don't open. Why do you open?
Thank you. Okay. Right, you drew that? Let's continue. The latent heat L. Whoops. Now, this is a definition which most students get wrong in the exam because they forget to say something. But the latent heat of a material is the energy you need to change the state of the material and then this is what everybody forgets to say, it's the energy you need to change the state of the material, but not change the temperature. So latent heat of a material is the energy required by a unit mass of the material to change its state to a different state without changing its temperature. So it's how much energy you need to only change the state, not to change the temperature. Got that? Yeah? Okay. Continue? Okay. Yeah? Are we just waiting for Bruce? Waiting for you? Just waiting for Bruce? So you have latent heat is to change a state, but you actually can be more precise. We can say latent heat of fusion. So what state change do you think that is? If you think about the word fusion, you might be able to guess. Which is it? Solid, liquid, gas. Which? It's like ice to water. So it's solid to liquid or liquid to solid. It's this way around. So it's energy required for melting, basically. And then the other one, latent heat of vaporization. Yeah, so boiling. Yeah, okay. Please write those words down, fusion and vaporization.
Did they ask for definition?
Of which? These two? No, they just use them in questions.
What's the word from the repeat to ice?
From liquid to ice? For this? Fusion? Yeah, the direction is not important for the energy. Okay, continue. Yep. So, we can make a formula now from this definition. The energy required to change the state is simply the energy required to change the state of mass m of a material, but no change in the temperature, is simply ml. So the latent heat value multiplied by the mass. That's how much. Where do I go from Q to delta Q? The energy required to change the state is just ml, where L is the latent heat and m is the mass. So it's a simpler formula even. So if we can write this formula down, ml. Yeah. Who's the M? I'm the M. Doesn't matter. What, the material? Yeah. Okay, continue. You got that formula? Alright. So, just to be clear about something here, water will freeze at 0 and water will boil at 100. You know this. Now time for some values. The latent heat of fusion for water is 334 kilo. Please remember the kilo. So it's 334,000 joules per kilogram. So that's for water, which you'll need for today.
We should know that.
No, they'll give it to you in the exam, but you'll need them for the questions. Got that? Yeah? Okay. The next one, of course, is vaporization, which is much, much bigger. It's 2,265 kilo joules per kilogram. You got that value? Yeah, continue. Yeah. Note that sometimes students get a bit confused about this fact, but just to make it clear, water could be a liquid at 100. Just because water reaches 100 Celsius doesn't mean it instantly turns into steam. While it's at 100, it still needs to get enough energy to become steam. Until it does, it actually will still be a liquid. So water could be a liquid at 100. In fact, it is a liquid at 100 and will stay a liquid until it gets enough energy to become a steam. Likewise, water could be at 0 Celsius until it loses enough energy to become ice. So what's interesting about 0 and 100 is that at 0, it's possible for it to be ice or water, and at 100 it's possible to be water or steam. So these temperatures, they kind of overlap. The states, the ice could be 0 and the water could be 0. It's possible for it to be one or the other. And sometimes students think, oh, it's 0, so it must be ice. No. If it's 0, it could be ice, but it could still also be water. So just to be really clear again, imagine a block of ice at -20 and you slowly heat it in a microwave. What will happen? Well, first it will be -20 and then it will increase to 0, but it will still be ice at 0 until some time passes and then it melts and it becomes water at 0. And then what happens next? It heats up until it becomes water at 100. But then some time will pass while it's at 100 and it's turning into steam. And then what will happen next? The water is now steam at 100 and now the steam will start to warm up and go past 100. Okay, you don't need to write this down, I just want you to get the picture clear in your head. But I think you all have it clear. So let's have a look at an example. So, how much energy do you need to change 1 kilogram of ice into 1 kilogram of steam? So, going from 0 to 100. So this is just using the calculator here. I'd like everybody to try and bash in the numbers. So we want to go from a kilogram to ice at 0 to a kilogram of steam at 100. Okay, did we get an answer?
Yeah.
Well, let's do it together. So, first things first. It starts off as ice at 0, and then it becomes liquid water at 0. So how much energy do we need there? What formula do we use? Do we use mc delta theta, or do we use ml? ml. And what's the m here? 1. And what's the L for fusion? 334 kilo. Now, what happens next in the process? The temperature increases from 0 to 100. What formula do we need for that? mc delta theta. So m c delta theta, which is 100. Finally, it goes from liquid water at 100 to steam at 100. So which formula do we need for this? ml again. But this time the L is different because it's vaporization. So what's the L for that? 2265 kilo. So this answer should be pretty big. Yeah. It's 3 megajoules about. Yeah. 3 megajoules? That's a lot. That's a lot. So to change ice into steam is 3 megajoules. Okay. Got that? Question? No? Okay. Continue? Is it 30 or is it 3? Hang on. 3 megajoules. That's what I got. Yeah. Continue? So, next now. A 200 gram cup of water has 10 grams of ice in it, added to it I mean, and they're mixed together until they reach thermal equilibrium. How much energy will be required to bring the mixture to 10 Celsius? Now think about this. I don't tell you what the temperature is at the beginning, but I'm asking you how much energy do you need to bring to 10 Celsius. So I don't tell you what the temperature is at the beginning, but I kind of tell you in a sneaky way. I tell you have 200 grams of water, you add in 10 grams of ice, and you mix it until it reaches thermal equilibrium. Thermal equilibrium means it's at a constant same temperature. So there's only one temperature that it could be at. What temperature is that? Well, it can only be 0 Celsius. Why is that? Well, if the ice and water are mixed together until they're the same temperature, there's only one temperature that ice and water can share, and that's 0. The ice could be less than 0, but then it wouldn't be the same temperature as the water. And the ice could be more than 0, but it wouldn't be ice anymore. So 0 is the only possible temperature that the ice and the water can both be at the same time in the cup. I don't know if you are happy with that. Some of you don't look happy with that.
If ice is melting in milk.
Yeah, well that's the next part. Now I say the ice begins to melt.
Then water should be existent and ice should be existent at the same time.
If it is past 0, then it can only be water, liquid water. I mean, you can't have a cup of iced water more than 0, because the ice can only be ice up to 0. You don't look happy with this. Are you happy with this or not happy with this? You definitely don't look happy with this. You're not happy with this? You can be honest with me. I won't take it personally.
If this water, I put some ice.
If you put some ice in that,
yeah,
and mix it together, and you still have ice in it,
yeah,
and they're all the same temperature now,
yeah, so temperature is 0.
It has to be 0. It has to be 0, yeah. You see, but you look so unhappy with this. Like, you don't believe me. I can tell. I can tell from your face you don't believe me. What are you thinking?
But like, if you put ice inside, then after that, like the when you drink something, when the ice on top is cold, but then the bottom part.
Yeah, that's why I said they're mixed together. So you have to give them a good mix. Because of the reason you said, it's possible that the ice on the top is 0 and the water down the bottom is actually warmer than 0. In fact, that is what usually happens. If you have ice in your glass of water, on the top will be 0 and on the bottom will be like 4 Celsius maybe. So that's why I said they're mixed together, so that it's all the same temperature. Anything else?
Why do you want us to use the ice?
What do you mean?
Where is it mentioned that the ice should stay as ice?
I suppose because I said they're mixed together and reach thermal equilibrium.
Yeah.
So I guess I'm trying to say is that you mix them so that they're both at the same temperature. So it means that I'm still talking about having both. It's only in the next sentence where I talk about it now changing into something else. How much energy do I need to bring it to 10? Well, if it's at 10, then it's no longer ice and water. It's only become just water then, yeah. Will we try this one now? We'll see what we get. So, let's draw what we have here. So, here's our water and here's our ice. So, we have 200 grams of water at 0. And we have 10 grams, and this is ice, at 0. And then what happens is this increases to 10, and this increases to 10. And the question is, how much energy do I need to do this? Yep, so let's calculate this. So first, let's look at the water. That's kind of the easy one. The water begins its life at 0 and increases to 10. So what's the formula I need for the water? MC delta theta, which is 0.24181 10. That's for water. Now let's have a look at the ice. And then we'll add the answers together and this will give us the total. Okay, the ice is a little bit harder. So it begins its life as ice at 0 and ends as water at 10. So first it has to melt. What's the formula for that? ml. So in this case, it's ml. And then after it melts, what happens next to it? Yeah, it becomes water and then it gets warmer. So then we also need a plus mc delta theta. So that's actually, you can simplify that as just m L plus c delta theta, which will be 0.01. What is the latent heat of fusion? 33. No, that's not. Oh yeah, okay. 334,000 plus 4181 times 10. Okay, so if you can please calculate this and add them together, we get our answer. Got a number? Go for it. What's your question? What do you think before I tell you?
I'm not sure.
But if you had to choose, what would you choose?
Maybe ice.
Oh, sadly you should have gone with water. Because what happens is, the ice is at 0, and then the first thing that happens to it is it's ice at 0 and then becomes water at 0. And then when it's water at 0, it becomes water at 10. So you have to use the C for water because it's changing its temperature when it's a water, not when it's an ice. So that's why I use 4181. Does that make sense for you? Is that okay or not?
Yeah.
Are you sure?
Yeah.
Okay. What answer did we get here?
12.1.
Say again?
12.1 kilojoule.
12.12
1 kilojoule.
what?
1 kilojoule.
12.1 kilojoules. That's not that much. Okay. That's how much energy you need to do this. Continue? Right. This is a little bit harder. You have some ice at 0 and you mix it with water at 15. 330 grams of water at 15. The ice and water was mixed until the ice melted and the final temperature was 5 Celsius. How much ice was added? So what you've got here is, you've got a cup of water at 15, you put some ice in it, and you keep mixing until all the ice has melted and become just water. And what you're left with at the end is a cup of water that is now only 5 Celsius instead of 15. How much ice was required to do this? So let's try and work this one out. Let's draw what we have here. So I'll draw it here for you. You have water, 330 grams at 15. You put in some ice, which we'll call X grams, or maybe I'll just call it X kilograms, at, I'll tell you what, yeah, at 0. And you put this in and you mix it until you're left with 5 Celsius at the end. And my question is, what's the X here? How much ice did you need to add to the water to do this? Yeah? Shall we do this one now together? So again, we need to be clear about who's gaining and who's losing here. So we have two things. We have ice and water. So is the ice gaining or losing energy? Gain. And the water? Losing. So the energy which is gained by the ice will equal the energy which is lost by the water. Okay, so what happens to the ice? So let's calculate the ice first. So first it's ice, and then what happens next? It becomes water, and then what happens next? It increases to 5 Celsius, yeah. So what's the formula for the ice? That would be ml, which is 334 kilo. And then after the ice has melted and becomes water at 0, it then increases to 5. So that's mc delta theta. Now the gain in the temperature of the ice will have to equal the energy lost by the water. So what has happened to the water? So it's decreased from 15 to 5. So that's m c delta theta. What's the delta theta? 10. Okay, so this doesn't actually look too bad. You can actually solve this as 0.33 times 41810 over 334000 plus 5 times 4181, and we have the x. Problem? No? Can you type this up, please? Thank you. Don't trust him now, he might not get it right. No. Well, he does have a better calculator. This is the Malaysian calculator, isn't it? It's what's common in high school. Yeah.
I lost this one, so that is-
Oh, heartbreaking. Did you get an answer over there?
No?
What? 0. So that's 38.9 grams. Do you have a calculator over there? But you do have one, right? Yeah, okay. Right, is this one okay? It's not too bad. Continue. Yeah. Okay. Water of mass 250 grams was added to a copper calorimeter, which just means a copper cup, of mass 25 grams. The water was stirred until the water and copper were in thermal equilibrium. The temperature X was recorded. An electric heating element was placed into the water. It took 2 minutes for the 5.5 kilowatt element to boil off the water. Assuming no heat loss, what was the initial temperature? Alright, so let me just draw this because there's a lot going on here. This question says you start with a copper cup. So this is copper of 25 grams at some temperature we don't know, X Celsius. And then in it you put some water. And it's water of 250 grams at some temperature we also don't know, X, the same temperature. Then what you do in the story, I want my colours. Oh, yes. Give me a nice red. Yeah, it's not a nice red, but it'll do. Then you heat this up using a 5.5 kilowatt heater. And then after 2 minutes? Yeah. After 120 seconds, all of this water has turned into steam and there's no water left inside of it. So my question is, what's X? So this one's a bit hard. Let's try and do this one together. So the first thing we should do is use the power formula, because we can say power equals work over time. Now what do we know? Do we know the power? Yes. And do we know the time? Yeah. So we can say work equals power multiplied by time. So that is 5.5 thousand, because it's kilo. So what do we get here, please? 66.
Yeah. 110.
One more zero?
Yeah.
Okay. Now why is that helpful? Well, we can now calculate what was the work done by using the other formulas. So, three things happen. The copper gets warm, the water gets warm, and the water turns into steam. Okay, let's begin with the copper getting warm. So what's the M for copper?
0.025.
And what's the C for copper? 385, is it? And what's the delta theta for copper?
100 minus.
Good, 100 minus X. Because at the very end, the copper will be 100, because the water inside is boiling at 100, and the two will be at the same temperature. Yeah. Now, in real life, that might not be the case. It might be a different temperature, but for us, we'll say it's the same. 100 minus X. Okay, now let's look at the water. What happens with the water? Well, first we have M, which is 0.25, C, and then delta theta, which is 100 minus x. And then finally the water has to change into steam, which is mL. So that's M25L. And what's the L here?
Oh, no, it's
Check. 2265?
Yeah.
Okay, and this should equal 660000. Yeah? Okay, so let's make this a little bit easier. So you notice what's nice here is we have 100 minus x here and 100 minus x here. So we can take this out. And then we're left with 0.025 times 385 plus 0.25 times 4181. And then what you can do here, look, you can take this one to the other side. So on the right you can have 660000 minus 0.25 times 2265000. So actually you realize all I need to do is take this and put it under. And then after you divide it, well, it's 100 minus x, so then the x will be, if you rearrange it like this, x will equal 100 minus 660000 minus 0.25 times 2265000 over 0.025 times 385 plus 0.25 times 4181. So if we type all of that in, we will get what for x? 11? Got it? So how are we doing here? Ah, perfect. Did you write this down? Is that a yes? Continue? So just take 1 or 2 minutes just to have a look at and try maybe one of the questions in the worksheet before you go. I can close this?